Hello guys, this is Ayush Kumar Fabwani, registration number 22BCE1763. And today I'm going to be talking about the topic application of finite automata in search engines. So these are the contents: machine algorithms, we have regular expressions, we have lexical analysis, URL matching, and spelling correction. So in the string matching algorithms, first we take a look at how search engines process these vast amounts of text data, right? Finite automata are essential in creating efficient string matching algorithms that quickly locate and retrieve documents or web pages containing specific keywords or phrases. The Knuth-Morris-Pratt algorithm and the Aho-Korasik algorithm are prominent examples. So basically what we're trying to say here is that string matching refers to pattern matching. We take regular expressions and we try to find those exact patterns in the World Wide Web across web pages, and then the search engine gets those web pages, their addresses, and puts them in front of you as links. So you give keywords, you give queries, it forms expressions, and then uses those expressions for pattern matching, and then search. So the string matching automata is a very useful tool which is used in string matching algorithms. String matching algorithms build a finite automata scans the text string T for all occurrences of this said pattern T. The idea of this approach is to build finite automata to scan text T for finding all occurrences. This approach examines each character of text exactly once to find the pattern. Thus, it takes linear time for matching, but pre-processing time may be large. It is defined like a normal finite automata with 5 tuples: one for state in finite automata, one for input symbols, one for initials, one for final state, and then one for transition function. The transition function being the normal one, following all the rules of a finite transition function of a finite state automata. These are all the details of what conditions these again the transition function should satisfy of a finite automata. Now, if we were to implement pattern matching for CAGA, we can see this finite state automata, finite state machine having 8 states from 0 to 7. You see, when you get an A, you move from 0 to 1. If you get another A or n number of A, you keep looping on 1, because every A now starts as a new pattern. So you take that A, then you get C, you move to the next one, you get another A, you move to 3. If you get A again, you move to 1, because now again you're starting again. Your pattern does not match the one initially given, but you are on A. So you are starting again with 1A. Again, you get a C. From 3, you move to 4. Then from 4, you move to 5, getting an A. Then from 5, you get A, you move back to 1. Then 5, you get G, you move to 6. 6, again, you get A, you get 7, which is the final state. If you get A, you move back to 1, because now again you're starting with 1A, you're starting a new pattern. On 7, if you get C, you move to 2, because now you've got 1A and 1C. You are working with that assumption. So that's how we would use finite state machines for pattern matching, which is a very important part of how search engines work. Now, to come to regular expressions. Search engines often allow users to use regular expressions in their queries, providing powerful and flexible search capabilities. Finite automata can parse and match regular expressions efficiently by constructing deterministic finite automata or non-deterministic finite automata representations of the expression. This enables users to specify complex search patterns such as wildcards, character classes, and alternations, and retrieve results that match those patterns. You see, again, you give queries, it takes those words, it makes patterns, it makes regular expressions, which are then implemented for a thorough search of the World Wide Web. To search through web pages to find the characters of the words that you want, and then sending those particular web pages to you as a response to your request. Regular expression uses meta characters in conjunction with a search engine to retrieve specific patterns. Meta characters are the building blocks of regular expressions. For example, /D is a regular expression in a meta character that represents a digit character. D stands for little character. You can use regular expressions to search for social security numbers, patent numbers, URLs, email addresses, and other strings that follow a specific pattern. There are several implementations of regular expressions. The differences in implementations usually include the way special characters are handled and how character classes are treated. To take examples, we're going to take a look at these codes. In the first box to the left corner, you see 4 letters, 4 digits, 4 letters, 4 digits. So it is a fixed pattern. So in the regular expression, we have A, Z, letters between A to Z, any 4 of them, then digits between 0 to 9, any 4 of them, again 4 letters, and again 4 digits. This is the simple regular expression. Then the second, we have 3 digits followed by dot, then 3 digits, 3 letters, dot, 3 digits, dot, 3 digits, dot, 4 digits, underscore 4 digits. Of course, the 3 digits are exact same, and the 4 digits are exact same. So we get a very simple regular expression. A to Z 3 forward slash dot 80 to 93 dot 0 to 93 dot 0 to 94 underscore 0 to 94. Then we come to lexical analysis. What is lexical analysis? Lexical analysis is basically breaking down of the given text. Finite automata are used to create tokenizers that break down the input text into a stream of tokens. These tokens, representing words or phrases, are then indexed and used for efficient searching. Finite automata help in recognizing and isolating words while also handling special cases like punctuation, white space, and tokenizing compound words. See, we do this in NLP as well. We do it across various machine learning. So basically, what we're doing is we're breaking things down so that they're easier to analyze. We take a long set of data, we use predefined regular expressions, predefined patterns to match this data to these patterns and break them down, so that you can better analyze them. You understand that certain parts mean something, certain parts mean something. Together they have context, but separately you can take a look at them individually and then you can assess them, which will be difficult to do in a big data. So we use tokenization. So, we go through the whole process of how actually this tokenization works using finite state automata. So lexical analysis is the first phase of compiler, also known as the scanner. It converts the high-level input program into a sequence of tokens. Lexical analysis can be implemented with deterministic finite automata. The output is a sequence of tokens that is sent to the parser for syntax analysis. So again, to go through the entire process now, number one, input pre-processing. This stage involves cleaning up the input text and preparing it for lexical analysis. This may include removing comments, white space, and other non-essential characters from the input text. You can use finite state automata to traverse through the whole string, and then, for example, this is a simulation. You from one state to next state, if you get a space, you don't move. You don't go to the next state. You keep looping on the same state, and you move to the next space and state until you get a proper input symbol. This could mean that you remain in the same state until you get a space. So you're not recognizing it, you're removing it completely altogether. This is an example you could use. Now, tokenization. This is the process of breaking the input text into a sequence of tokens. This is usually done by matching the characters into the input text against a set of patterns or regular expressions that define the different types of tokens. Now, when you're doing finite state automata, you're using finite state automata, you define regular patterns, and as we saw, how can you do pattern matching? You take regular expressions, you try to pass every word through a FSM that is defined for that regular expression, and if it passes, reaches the accepting state, and of course you say that okay, this matches the given pattern. Now you use predefined regular expressions to tokenize things, to break them down. Token classification. In this stage, the lexer determines the type of each token. For example, in a programming language, the lexer might classify keywords, identifiers, operators, and punctuation symbols as separate token types. So now you see here, once you've broken things down, you also need to classify them, because of breaking things down, we've lost the context. You need to maintain context to actually work with things. So you put them into categories, so you know what token means what, is intended to do what, is a product of what, and so on and so forth. Token validation. In this stage, the lexer checks that each token is valid according to the rules of the programming language. Here, because here we are working with examples of having a code in a programming language, then you're trying to break it down. Output generation. In this final state, the lexer generates the output of the lexical analysis process, which is typically a list of tokens. This list of tokens can then be passed to the next stage of compilation and interpretation. Now we come to URL matching. What happens in URL matching is, URLs follow a very strict pattern, as we all know, right? This pattern can be made into a regular expression, and then using finite automata can be employed to create URL matching algorithms. So to take a look at this, search engines require efficient mechanisms for matching URLs with specific patterns or keywords. Finite automata can be employed to create URL matching algorithms. These algorithms enable users to search for web pages based on the URL structure or content, such as searching for all web pages within a specific domain or containing particular keywords in the URL. Spelling correction, the last topic that we discussed. Now, spelling correction using finite automata is a crucial aspect of search engines and text processing applications. Finite automata are employed to efficiently suggest and apply corrections to user queries. Making search results more accurate and user friendly, finite automata is used in mostly four stages of the process: dictionary creation, edit distance, fuzzy matching, and suggestion ranking. So number one, dictionary creation is basically you create a data structure that has all the words. You need to have words, a set of words to go through for pattern matching, right? What are you going to apply the pattern matching, or what are you going to pass through input through this FSM? So for that, you need dictionary creation. You need the set of words. Then you have edit distance. Again, an application of finite automata. You go through the whole data set to create an edit distance. Fuzzy matching. What is fuzzy matching? So up until now, when we were doing pattern matching, we were doing an exact match. For example, the ACA example we took, the letter example, you were matching it exactly. Fuzzy matching is you match similar items. You match everything that is similar to the given pattern. So that's fuzzy. So not clear, basically, right? Then we have suggestion ranking. Again, a very clear application uh, of finite state automata. So if we were to take a look now, we have gone through quite a few applications. First is string matching algorithms, which employed a finite state automata heavily to match each and every expression to the given pattern. So this is employed in searching through the World Wide Web, to employing through millions and millions of pages, find words that match these patterns, and then bring these pages to you. Then we looked at an example of how pattern matching is actually being done. Then we saw regular expressions. Now we saw pattern matching. How do you employ this pattern matching? You create regular expressions. You give queries to the search engine. It creates a pattern for that. It creates a regular expression for that. Then it passes on to creating a finite state machine that can be used for finding these words that satisfy these regular expressions, right? So regular expressions are used heavily. We saw how these can be made. Lexical analysis, breaking down, because again you cannot pass a whole data set into these FSMs. You need to break it down. And again, breaking down this lexical analysis can be implemented with deterministic finite automata. The output is a sequence of tokens that can be sent to the parser for syntax analysis, again which uses finite state automata. URL matching follows strict pattern, can be used for is used with the help of regular expressions to match, and is employs finite state automata in its matching heavily. Spelling correction, you find words that match a certain pattern. Your spelling is wrong. It tries to find a word in the dictionary that it has created, which is similar to this, closest to this. It finds the distance that it has. Distance in the sense, suppose you have a word A, B, C, D, E, and then it is closer to a word A, B, C, D, F. But it can be A, B, C, D, DEE, right? So which it is closer to in this dictionary, that word it will round up to. It will go to that word. It will become that word, right? So you're finding edit distances. Fuzzy matching, you're finding all the similarities. On base of that, you're finding a match, and then suggestion ranking. Finite state automata is used in selecting the suggestion that is most likely in spelling correction. So that was it. Thank you. This is Ayush, and this was my presentation on application of finite state automata in search engines. Thank you for watching.